magnetite nanocubes as biomedical application agents. So most of you probably know that iron oxide nanoparticles have been used in cancer diagnosis and therapy for many years. Like you can use it in diagnosis as, for example, MRI, relaxation, T2 relaxation, as magnetic particle imaging. You can also use it in drug delivery, where you can attach drugs to the nanoparticles, and then using magnetic fields, you can guide them. And then another topic that's very popular nowadays is localized hyperthermia using iron oxide nanoparticles. Most of the studies have been done in using magnetic fields, like I show here. But you can also use iron oxide nanoparticles to using light to induce hyperthermia, as I will show you later. So what's the status in the real world? So actually there has been several commercial MRI contrastation using iron oxide. And magnetic hyperthermia has already been tested in humans in phase 2. However, not everything is perfect. In fact, the commercial production of MRI contrastation used based on iron oxides have been stopped, mainly because they cannot compete against the gadolinium-based ones. And also, magnetic hyperthermia is still being continued in hospitals. But the problem is that you need very, very high dose of iron, or iron oxide in this case, to get reasonable results in the hospital tests. So how can we improve the state of the art, especially in magnetic hyperthermia? One thing has been proposed is doping iron oxide with cobalt. Actually, cobalt can improve the magnetic properties of the nanoparticles. And then another option has been combining magnetic hyperthermia with optical hyperthermia by adding plasmonic materials into iron oxide. So then you can combine magnetic and optical hyperthermia in the same nanoparticle. However, things are not as good as they look, because first, cobalt has not been approved to be used in humans. And actually, there's studies that show that adding cobalt in biomedical nanoparticles can lead to destruction of the cell. So you have to be careful when you use cobalt in your biomedical nanoparticles. Actually, iron oxide is the only magnetic material approved by the FDA and the European Medical Association to be used in humans. In the case of combining optical heating and magnetic heating, this can be done, but the problem is that iron oxide and gold, which is the only plasmonic material that can be used in humans, are very difficult to combine because they have very different structures. So usually the properties, the final properties, are not as good as the individual properties of the two materials. So is there any other way to improve the properties? So we thought we can go into tuning the shape of the nanoparticles, rather than doping or adding other moieties into it. In fact, most of the studies done so far are done in spherical nanoparticles. So what we are going to study is if cubic nanoparticles can improve the properties of these iron oxide biomedical agents. So most of the cubic recipes to grow Fe3O4 are based on either iron oleate or iron acetylacetonate as precursor. However, both approaches have drawbacks. Iron oleate is a two-step process, and as such is time-consuming. But also it has another problem. Is that first it's difficult to grow particles larger than 20 nanometers, and they are prone to form FeO as a core rather than homogeneous Fe3O4, and then you need the next step of annealing to oxidize the whole particle, which also leads to defects. Here I show you a particle with a core of FeO and a shell of Fe3O4 grown with iron oleate. In the case of iron acetylacetonate, first it's difficult to grow small particles, and then it's prone to shape inhomogeneity and a broad particle size distribution. Here I show you an example where we have here some cubic nanoparticles, we have some cuboctahedrons, here rods, and here we have irregular. So you have to be careful. If you cannot control the conditions, then you end up with these really messy aggregates and strange nanoparticles. So what I'm going to tell you today is a new synthesis pathway based on iron acetylacetonate. So since to use the nanoparticles in biomedical applications, their properties depend on both the crystallinity and the shape. So in order to grow some nanoparticles, we set ourselves a set of criteria that we have to fulfill. The first one is size monodispersity, that all the particles have the same size. Low aggregation, so they don't form clusters. The iron oxide has to be pure, in our case Fe3O4. It has to be highly crystalline. We have to be able to control the size, and we should have a well-defined shape. So to start, what's the main problem when you grow samples on using iron acetylacetonate? Is that usually the solvent that's used to do the synthesis is even ethyl ether. However, this material is unstable at high temperatures. And what happens is, during the synthesis, there is a reduction of the boiling point with time. You can see here, when the boiling point of the ventilator, as we increase the time, you see that it starts at 290, which is the temperature we need. However, the boiling point starts decreasing with time. And this leads to this inhomogeneity I told you about. Because the reaction temperature is changing with time. So at every given time, the conditions are different, so you get different types of nanoparticles. So the way we solve this is, rather than using dibenzyl ether alone, we combine dibenzyl ether with octadecene, which has a suitable boiling point. The problem is that iron acetylacetonate cannot dissolve in octadecene, so then we cannot use it. So then we have to keep some dibenzyl ether to be able to dissolve the iron acetylacetonate. But octadecene has a slightly too high boiling point. That's why we add tetradecene to have a somewhere intermediate boiling point. And when we mix these three solvents, you see that the boiling point of the mixture is highly stable over time. So in these conditions, we are sure that the synthesis conditions are kept constant during the whole synthesis. So can we make cubic nanoparticles? Yes. You can see here that we have nice cubes with a very narrow particle size distribution, in the case about 16 nanometers. They are highly crystalline, and they are also very homogeneous. So how do we know they are Fe3O4? We did a series of tests. First, we measured the magnetic properties, and we see that the saturation magnetization at room temperature is about 84 mg, which is what you expect for Fe3O4. Then we measure the magnetization versus temperature of these nanoparticles. And first, we see that the blocking temperature of the nanoparticles are about room temperature. And second, there is a decrease here of the magnetization at about 100 Kelvin. This is what's called the Verbeek transition. And this is unique to Fe3O4, like maghemite or hematite do not have this transition. And also, when we did the X-rays, and we get a cubic spinel phase as we expect, but also we get this peak at very low angles, which is characteristic of Fe3O4. And finally, we did energy loss, electron energy loss spectroscopy. And from the spectra we get at the iron edge, we can, for example, from the ratio of these peaks or all the other parameters, we can also determine that we have Fe3O4. Moreover, we did a mapping using this type of spectra at each point of the nanoparticle. And you can see here that the oxidation state of the nanoparticle is homogeneous all over the nanoparticle. You see here, like maghemite should have red dots, which we don't see here, or wurtzite should have also red dots, which we don't see. So we have a very homogeneous 2.65 oxidation state, which is what we expect for Fe3O4. So can we control the size? Yes. There is several ways to control the size. The easiest one is by changing the amount of iron acetonate we put in the reaction. And you can see here that we can change from about 10 nanometers to about 20, 25 nanometers. Here, note that in all the images, the length bar is the same, 100 nanometers. And then we tried another approach, which is instead of there is a previous step we use to grow the samples, which is a vacuum stage to remove the oxygen and the water from the precursors. And depending at what temperature we do this step, we can also control the size. And also a final approach we did to control the size is to change the heating rate, or change the amount of total volume of sample we have in the reaction vessel. And you can see that the maximum nanoparticles we can make are about 90 nanometers. So we can grow samples, cubic samples, with narrow particle size distribution from 10 nanometers to 90 nanometers just by playing around with the reaction conditions. And they all have very narrow particle size distribution. So in order to check how good they were, we had to think of a way to say how cubic they are. So then we went into this type of idea. A cube has a diagonal of a square root of 2 times the length. If you have a sphere, this diagonal reduces to 0.7. If you have a quadradron, this diagonal here reduces to 0.5. So we thought that this would be a good parameter to check how cubic the particles were. So as you can see here in black, particles from 10 nanometers to 90 nanometers keep a cubicity of 90% or even higher. So even if we can change the size by a large amount, their cubic shape is not compromised. Second, we checked how homogeneous were the particles. In this case, what we did is, this is a typical particle size distribution. So we check the standard deviation, which will be the width of this distribution, and we divide it by a particle size. This was what's called the polydispersity index. And usually below 10% is you are supposed to have a monodisperse sample. And you can see here that you have to look at this axis in this case. You see that all the particles, except the largest ones, have a polydispersity of less than 10%. So we can consider them as monodisperse. The only one that is slightly higher is the largest nanoparticle. So we can both control the narrow particle distribution and the cubicity, which is maintained over the whole size range. Then we check for the the stability of the nanoparticles. When they are synthesized, they are all stable. These are here. But when we wait 3 days with the nanoparticles inside the liquid, you see that the smaller ones keep stable even after 3 days, but the larger ones tend to precipitate. Even these ones, if we shake again the nanoparticle, shake the container, they will be again colloidally stable, but they tend to precipitate after a few days. So to check that, what we did is to measure the hydrodynamic ratio, which rather than measure the particles as we use in the TEM, it measures, if there is aggregates, it will measure the size of the aggregates. So here you can see in blue that as the particles are small, you have to look at this size, this is the hydrodynamic ratio divided by the TEM size. You see, for the smaller particles, this ratio is 1, since all the clusters are composed by 1 nanoparticle. However, as the particles become larger than 16, then the hydrodynamic ratio starts increasing, meaning that after a certain size, they start to agglomerate. To understand this, what we did is to measure the magnetic properties. And we can see that the nanoparticle with 15 nanometers has no coercivity at room temperature. Means this particle is super paramagnetic. But as we increase the size, the nanoparticles start having larger and larger coercivity, meaning they are ferromagnetic at room temperature. And when they are ferromagnetic, they tend to agglomerate. This is what this is telling us, that when they are super paramagnetic, the nanoparticles are colloidally stable, but as we increase in size, they tend to agglomerate and become ferromagnetic. So next we try some magnetic properties. So first we did some nuclear magnetic resonance studies. And you see here that as the concentration increases, the sample becomes blacker, meaning we have a larger MRI signal. But when we analyze the results, we see that when we go from 13 to 15 nanometers, there is a big improvement in the relaxivity. It goes from 322 to 455. But when we increase from 15 to 19, the improvement is very small. This is because these samples have a more magnetic moment, but since they tend to agglomerate, the improvement is very small. And also, if we compare our results to the commercial Fe3O products, these are more than twice better than the commercial ones, which are all of them are based in spherical nanoparticles. So from the point of view of nuclear magnetic resonance, using 15 nanometers nanoparticles would be the preferred size, since it has very good properties and they don't agglomerate. Next, we measure the magnetic hyperthermia, and we used very mild conditions, which are below the proposed limit to be used in humans, which is 10 to 9 amperes per meter second. And we use 3.1, which is about half of it. And we use a moderate amount of nanoparticles. Should we compare to the ones I showed you in the beginning that we used in clinical trials, which are 160, I think it was. So it's many times larger than this. And what we do here is we put our nanoparticles suspended in water, and then we apply an AC field and measure the temperature of these nanoparticles. So here I show you the evolution of the temperature with time, and you see that all the nanoparticles warm up as we put AC field, as we expect. But similar as we saw in the NMR, when we go from 13 to 15, which is only 2 nanometers difference, there is a big improvement in the properties, in the heating of the nanoparticles. And when we increase from 15 to 19, there is some improvement, which is different, which is 4 nanometers, some improvement, but not as much. And when we compare to similar nanoparticles, but spherical, they get far worse results than all the other cubic nanoparticles. So again, from the point of view of magnetic hyperthermia, then 15 nanometers would be preferred. So, as I told you, there is another approach to use aerosol nanoparticle, which is optical hyperthermia, using near-infrared light. This is usually done in plasmonic nanoparticles or materials like carbon or organic dyes. And there is usually two ranges of wavelengths that are used, which are called the biological windows, which is the wavelengths where the human tissues absorb less light. These are in the 800 nanometers range with the first optical window, and about 1100, which is the second optical window. Here, today I'm going to show you photothermia in iron oxide in the first and second biological window. The way we go about this is we shine the laser in our colloidal nanoparticles, and we measure the temperature of the liquid. And here we use much smaller concentration than the one I showed you before for the magnetic hyperthermia. It's about 30 times smaller, about 0.2 milligrams per milliliter. And we use very, very mild conditions, much lower than the maximum limit to be used in humans, which is about 1 watt per square centimeter, which we use 10 times less. And we see an interesting effect, which is when we use 808, which is the typical one most people use in iron oxide, which is in the first biological window, we do increase the temperature as expected, and when we switch off, it goes down. But when we use 164, which is in the second biological window, the heating is much better. And then what we did is we measured the optical absorption of magnetite, and we saw that actually magnetite has an optical transition at this wavelength, so the absorption increases. So it's more effective to be in the second biological window than in the first. And it's also interesting that maghemite does not have this transition. So the optical absorption is flat, and it has much worse absorption. So if we use maghemite, it will be much worse. Oops. So it is more efficient to use second biological window than the first biological window when we use iron oxide. So in conclusion, I hope I have convinced you that we have synthesized Fe3O4 nanocubes in a broad range of sizes with shade control and a good particle size distribution and with colloidal stability. And the nanoparticles exhibit excellent NMR relaxivity, a good hyperthermia response, and photothermal behavior in the near-infrared region. So to conclude, Fe3O4 nanocubes are great potential as have a great potential as versatile Theranostic agents. So thank you for your attention.